Okay, so in this video we're going to be reviewing how to apply boundary conditions, or what the boundary conditions are for the Navier-Stokes equations. Okay, so the Navier-Stokes equations, these are our partial differential equations that express conservation of mass and momentum for a fluid. And if we can solve these equations, we're able to get spatial distributions of velocity and pressure, right? The reason we need boundary conditions is that, ultimately after we apply assumptions and we simplify the equations, we're left with the second order ordinary differential equations. And if you remember from your previous math classes, whenever you have a second order ODE, you need to apply two boundary conditions in order to fully specify the solution, right? And so we're going to be left with a function after we integrate that has two arbitrary constants, and boundary conditions let us solve for those constants, right? And so physically, what boundary conditions are is that they define the physical state of the physical phenomenon at the boundaries of the domain. So it's a little bit of a tongue twister, but I had to keep it general. So more specifically for fluid mechanics, what this means is that our boundary conditions are going to define what the fluid is doing at the edges of the domain. Okay, and so you can see in the figure below we have flow in this looks like flow in a pipe, and so our boundary conditions are going to be defined what's happening with the flow, or what the flow is doing at the two walls that kind of contain the flow, right? And so our domain is, just whatever's inside the pipe, and the boundaries are the edges of that pipe, right? So mathematically, we just said this, that, whenever we solve second order ODEs, we need algebraic expressions to solve for the arbitrary constants, and the boundary conditions are what let us do that. Okay. Okay, so let's talk about the types of boundary conditions that you'll see for fluid mechanics for Navier-Stokes type problems. And so the first type of boundary condition is what we call the no-slip boundary condition. And so whenever a fluid makes contact with the solid surface at the boundary, what we say is that the fluid is going to stick to that boundary, right? And so because of the viscosity inside the flow, that's friction, right? The fluid is going to stick to that, and thus the fluid that's immediately right next to the solid, or the one that's touching the solid, will have the exact same velocity of that surface. Okay, and so often what you're going to have is you're going to have fixed walls surrounding the flow. So in those cases, the velocity touching the wall will be zero, because the wall is fixed, it has zero velocity, and so the fluid touching that wall will also have zero velocity. Okay, so mathematically that's how we do that. Another condition that you'll see, it's not as common, but it is out there, is when you actually have a moving wall. And so if the wall is moving, the no-slip boundary condition still applies, but now instead of specifying the velocity be zero, what we do mathematically is say that the fluid velocity has to match the wall velocity, right? So keep an eye out for that when you have problems with the moving wall, like this one below. Okay, so the other type of boundary condition you'll see often is what's called a stress condition. And so when the fluid in the domain is in contact with another fluid, then what we say is that the shear stresses of those two fluids must match. Okay, and so here at the bottom of the screen here, where I have, it's a very classical problem in fluid mechanics. If you have two fluids that don't mix, and to solve for the velocity distributions at that interface between fluid 1 and fluid 2, what we're going to impose is that their shear stresses are going to be the same, right? And so the shear stress is given by the viscosity multiplied by the derivative of the velocity. Okay. Another common case that you'll find often in practice is if the fluid is in contact with another fluid with a very, very low viscosity. So one common case is air. And so in those cases, the shear stress condition still applies, but because of the low viscosity, we can essentially assume that the shear stress there is going to be zero. Okay, and so this is common for when you have fluids that are exposed to air or exposed to the environment, right? So keep an eye out for that. And so in those cases, you can just set the shear stress equal to zero.